Have you ever stopped to truly think about time? It is the one constant in our lives. An invisible force that governs everything we do. From the moment we wake up until we go to sleep, time marches on. But here is the thing. It only ever moves in one direction. Forward. You cannot rewind it, pause it, or fast forward it. We all experience it, universally, as this relentless, irreversible march from past to future. But why? Why does time possess this fundamental asymmetry? Why can we not remember next Tuesday, only last Tuesday? Why do eggs break but never spontaneously reassemble? Why does a dropped cup shatter into 1,000 pieces, but those pieces never leap back together to form a whole cup again? This seemingly simple question hides some of the deepest mysteries of physics and our universe. Today, we are going to explore the fascinating reasons behind time's one-way journey. Welcome to Why and How. Scientists refer to this directional quality of time as the arrow of time. It is not just one arrow pointing forward, but rather a collection of phenomena that all conspire to give time its relentless forward momentum. We can broadly categorize these into three main arrows: the thermodynamic arrow, the cosmological arrow, and the psychological arrow. While they describe different aspects of time's direction, they are intricately linked and largely stem from one fundamental principle. Let us start with what many physicists consider the most fundamental of all, the thermodynamic arrow of time. This arrow is rooted in one of the most powerful and well-established laws of physics, the second law of thermodynamics. Now, do not let the fancy name intimidate you. In simple terms, the second law of thermodynamics states that the total entropy of an isolated system can only increase over time, or at best, remain constant. It never decreases. So, what exactly is entropy? Think of it as a measure of disorder, randomness, or the number of ways a system's components can be arranged. A system with low entropy is highly ordered, highly structured, and predictable. A system with high entropy is disordered, random, and less predictable. Let us use some everyday examples to make this clearer. Imagine you have a meticulously organized desk. All your papers are neatly stacked. Pens are in their holder. And books are aligned. This is a state of low entropy. Now, let an earthquake hit, or simply get busy working on a project, and soon enough, your desk becomes a chaotic mess of papers, scattered pens, and open books. This is a state of high entropy. The second law says that your desk will not spontaneously reorganize itself back into its pristine state. You have to actively put energy into it to reduce its entropy. Consider a glass falling from a table. It shatters into countless fragments. This is a transition from a relatively ordered state, an intact glass, to a highly disordered state, shattered pieces. The process of the glass shattering increases the entropy of the system. We never see shattered pieces spontaneously gather themselves, fly back up, and reassemble into a perfect glass. Why? Because the probability of all those individual molecules moving in exactly the right way at the same time to reverse the process is astronomically, mind-bogglingly small. It is not impossible in a strictly theoretical sense at the quantum level over tiny timescales. But on our macroscopic scale and for any observable period, it just does not happen. Think about an ice cube placed in a warm drink. The ice cube, a structured solid, melts and disperses its coldness throughout the drink, making the entire system a uniform temperature. This is an increase in disorder. The heat flows from the warmer liquid to the colder ice until equilibrium is reached. We never see the drink spontaneously separate into a cold ice cube and a warm liquid. This is because there are vastly more ways for the energy to be spread out high entropy, than for it to be concentrated in an ordered fashion, low entropy. The universe, as a whole, is one such isolated system, and its entropy is constantly increasing. Every process, every interaction, every event, from the simplest chemical reaction to the grandest stellar explosion, contributes to this cosmic march towards greater disorder. The thermodynamic arrow of time is essentially the direction in which disorder increases. And since disorder is always increasing, time itself appears to have a direction. This is why we cannot unmix cream from coffee, or uncook an egg, or unring a bell. These processes convert ordered energy into disordered energy, making them irreversible. Next, we have the cosmological arrow of time. This arrow relates to the expansion of the universe itself. According to our current understanding, the universe began about 13.8 billion years ago with the Big Bang. At that incredibly early stage, the universe was in an extraordinarily low entropy state. It was incredibly hot, dense, and uniformly packed with energy. In a sense, it was highly ordered. As the universe expanded, it cooled and became less dense. This expansion provided more space for matter and energy to arrange themselves in different ways, leading to an overall increase in entropy. Galaxies formed, stars ignited, Planets coalesced, and complex chemical reactions took place. All these processes increased the disorder within the expanding cosmos. The cosmological arrow points in the direction of the universe's expansion. If the universe were to eventually stop expanding and start contracting, a hypothetical Big Crunch scenario, then the cosmological arrow might reverse. However, current observations suggest that the universe's expansion is not only continuing but accelerating. This suggests a future where the universe will become increasingly dilute and cold, leading to what is sometimes called the heat death of the universe, a state of maximum entropy where all energy is evenly distributed, and no further work can be done. So, the expansion of the universe acts as a gigantic backdrop, facilitating and reinforcing the thermodynamic arrow, giving time a cosmic direction. Finally, let us consider the psychological arrow of time. This arrow is perhaps the most personal and immediate, as it deals with our subjective experience of time. Our brains are remarkable organs, but they too operate under the influence of the thermodynamic arrow. We remember the past, not the future. We can anticipate the future, but we do not have direct memories of it. This is because memories are essentially records of past states of our brain. When we form a memory, we are creating a new, more ordered pattern in our neural networks based on past experiences. Accessing these memories involves processes that also increase entropy. Our entire perception of cause and effect is built upon this forward progression of time. We understand that striking a match causes a flame, not the other way around. We drop a ball, and then it hits the ground. This sequence is fundamental to how we learn, plan, and interact with the world. If we could remember the future, our understanding of free will and causality would be fundamentally challenged. Imagine knowing every decision you would make before you made it. That would dismantle our very sense of self. The psychological arrow of time is inextricably linked to the other two. Our brains process information and store memories in a way that is consistent with the universe's general increase in entropy. We build mental models of the world based on sequences of events that go from a cause to an effect, which is the direction of increasing entropy. It is hard to imagine consciousness existing in a way that perceives time flowing backward or being entirely reversible, as our very existence and ability to process information rely on consuming energy and increasing disorder in our local environment to maintain our own complex, but temporary, order. So, why does time only move forward? It boils down to probability and the fundamental tendency of the universe towards greater disorder. The second law of thermodynamics is a statistical law. While it does not forbid individual particles from briefly reversing their entropic path, on the scale of everyday objects and the universe itself, the probability of things spontaneously becoming more ordered is so infinitesimally small as to be effectively zero. We live in a universe that began in a highly ordered, low-entropy state and is relentlessly moving towards a state of maximum disorder. This cosmic progression is what defines the direction of time for us. Every breath we take, every star that shines, every thought we think, is part of this grand, irreversible journey. We hope this journey into the arrow of time has illuminated some of the universe's fascinating secrets for you. If you found this explanation helpful, please consider giving this video a like. We would love to hear your thoughts, questions, or perhaps even your own experiences with the perception of time. So leave a comment down below. And if you want to keep exploring more incredible questions about why and how the world works, be sure to subscribe to our channel for more educational content. Thanks for watching, and we will see you next time.